Hi everyone, welcome to the part 3 of the flipped classroom lecture on ophthalmic preparations. This video lecture will continue to discuss several important aspects in formulating ophthalmic products. Aside from the demonstrable efficacy of the product as we discussed before from various aspects of formulation, sterility is the most important issue given the route of administration of ophthalmic. The manufacture of sterile products, like ophthalmics, is not straightforward and microbial contamination control needs to play an essential role. There are severe risks for patients if sterile products become contaminated. Risks to patients with ophthalmic products include serious infection, blindness, and even death. Ocular infections and loss of vision caused by contamination of extemporaneously prepared ophthalmic products have been reported. Enhancing the probability of sterility is gained through environmental controls during manufacturing. Sterility is usually achieved through sterilization. You may now wonder why we would need a sterilization if a preservative is used. The answer is simple. Thinking of the aspect of sterilization, the product will not sterile after first opening as it exposed to the atmosphere. Preservative plays a role in maintaining the sterility after the opening. Also, preservatives may not kill spores. So sterilization is still in need. Sterilization for sterile pharmaceutical preparations including ophthalmic product can be achieved through various methods including autoclaving, aseptic filtration, gaseous sterilization and ionizing radiation. You will be taught in more details for different types of sterilizations later. BPC has listed 3 common sterilization methods for ophthalmic products. BPC methods A, autoclaving, and C, heating with bactericide are sterilization involving heat. However, BPC method B is the only sterilization without heat and it involves a transfer of aseptic filtered solution into the final sterile container using aseptic technique. It usually occupies a sterile syringe with a sterile filter membrane of your choice. The 2 membranes listed here are those typical pore sizes used. One thing to remember is that this method is conducted in a sterile environment and everything used must be sterile. This ensures the end products are sterile. The next slide will show you a short video of aseptic filtration in a real setting.
This is the proper procedure for the sterile ophthalmic drops that we'll be making in lab. You'll be receiving a pre-weighed bag of pilocarpine powder, 0.6 grams. You'll be receiving a bacteriostatic vial. We'll have a small beaker, our eyedropper bottle, and our 0.22 micron filter. So I have wiped down all my products. I have sprayed my gloves. So the first thing I'm going to do is I'm going to withdraw 9.4 mils from the bacteriostatic vial. Again, this is just using the basic positive pressure technique that we've been using. So I'll be putting 9.4 mils of air into my syringe. My bevel up, keeping my direct airflow. This is a horizontal airflow that I'm working in. Take my beaker, empty the contents of the bag into the beaker of the pilocarpine powder. going to saturate and dissolve the powder with the bacteriostatic solution. Gently mix it. While I'm waiting for it to dissolve, I can prepare my eyedropper bottle. So you would never insert a needle into the tip of an eyedropper bottle because it will damage the plastic plus change the drop size of the bottle. So you want to ensure that that's consistent for the patient who's receiving the eye drops. So you can do one of two things. You can take the lid and gently snap back and take the tip off the bottle, or you can remove the cap, take an alcohol swab, and gently remove the tip manually, like that, and just rest it on your alcohol swab. So once your powder's been dissolved, you can withdraw your solution from the beaker, almost like an ampule. You're just going to withdraw all the solution. So if I've added 0.6 grams of powder plus 9.4 mils of bacteriostatic solution, my final volume should be 10 mils, approximately 10 mils. So I have my 10 mils. I'm ready just to insert my filter. I'm going to take off my needle, attach my filter. This is a critical site. When you open the package, this is the critical site. So you want to ensure that you do not touch the critical site. Attach the one end, and you'll insert a needle to the other end. That's the other critical site. Okay. And then you're ready to filter your solution into the eyedropper bottle. Again, don't force the solution through the filter. Just gently press down on the plunger. Return your tip cap to the eyedropper bottle. Put that back on. So now you want to ensure that your filter was intact while you were filtering the solution into the eyedropper bottle. So you can do one of two things. You can try to pull down on the plunger, and you should feel resistance. You can't pull air into the filter. Also, you can draw air into the syringe, and you will not be able to push that air through. You'll feel resistance. The air will not pass through the filter. So that means your filter has been intact the whole time. If I was able to pass air through the filter, that means the filter has been damaged, and that product should be refiltered. You would receive a proper label to attach around your eyedropper bottle indicating the drug, possibly even the patient's name, and then it would be a properly labeled product.
Eye drops have a disadvantage where it will easily escape from the eyes once applied. One of the ways to avoid this problem is to increase the viscosity. This will increase ocular contact time with a lubricating or moisturizing effect. Not only that, it can be instilled easier to the eyes. Viscosity adjusting agents will also increase the stability of suspensions. Hydrophilic polymers are the common examples here, such as methylcellulose or HPMC. You may use polyvinyl alcohol, PVA, polyvinyl pyrrolidone, PVP or polyethylene glycol, PEG. After all, what we have been discussing is really to maintain the stability of ophthalmic products. Apart from those discussed, for examples, the stability of active ingredients, excipients, vehicle, sterilization etc., there are a few more things we can do to help to stabilize the system. For example, we could add additives or stabilizers to slow down the degradation of ingredients. In many cases, actives are sensitive to the atmosphere, especially in the presence of oxygen, as it fastens the oxidative degradation. In this case, we could use antioxidant like sodium metabisulfite or sodium sulfite. Let's discuss sodium metabisulfite. It is suitable for acidic preparations or drugs because its efficacy is the highest at the acidic pH. It also has antimicrobial and preservative properties at acidic pH. The use of sodium metabisulfite also has a synergistic effect with nitrogen gas and ether. Despite it is good for acidic drugs, it may have interactions with some of them. For example, adrenaline, and phenylephrine. On exposure to air and moisture, sodium metabisulfite is slowly oxidized to sodium sulfate with disintegration of the crystals. Addition of strong acids to the solid liberates sulfur dioxide. In water, sodium metabisulfite is immediately converted to sodium and bisulfite ions. Aqueous sodium metabisulfite solutions also decompose in the air, especially on heating. Solutions that are to be sterilized by autoclaving should be filled into containers in which the air has been replaced with an inert gas, such as nitrogen. The addition of dextrose to aqueous sodium metabisulfite solutions results in a decrease in the stability of the metabisulfite. The bulk material should be stored in a well-closed container, protected from light, in a cool, dry place. It is incompatible with phenylmercuric acetate when autoclaved in eye drop preparations. Sodium metabisulfite may react with the rubber caps of multidose vials, which should, therefore, be pre-treated with sodium metabisulfite solution. Sodium sulfite is another antioxidant which is suitable for alkaline preparations. Iditate disodium or ED2 is a chelating agent used in a variety of non-ophthalmic products, including hair conditioner, facial cleansers, aftershaves and deodorants. In the recycling industry, it has been used to recover lead from used lead-acid batteries. In the medical field, uses include the treatment of acute mercury poisoning, lead poisoning and hypercalcemia. ED2 has gained use in ophthalmic solutions owing to its ability to bind metals. ED2 has been used in eye washes to aid in the neutralization of calcium hydroxide or lime burns to the cornea. Iditate disodium also has preservative effects based on its ability to chelate. When added to topical medicines in low concentrations, ED2 has been shown to inactivate trace amounts of heavy metals, which aids in the preservation of the solution. It is thus has a synergistic effect with benzalkonium chloride and chlorhexidine acetate. Iditate salts are more stable than idic acid. However, disodium iditate dihydrate loses its water of crystallization when heated to 120 degrees Celsius. Aqueous solutions of disodium iditate may be sterilized by autoclaving and should be stored in an alkali-free container. The use of ED2 may not be suitable for preparations with mercurial compounds such as PMN or thiamosyl. Stability of a product is also judged from the aspect of the packaging use. Traditionally, ophthalmic liquid products were packed in glass containers fitted with an eyedropper. Today, glass containers have limited use where product stability or compatibility issues exclude the use of flexible plastic containers made of polyethylene or polypropylene. Most liquid ophthalmic products on the market are packaged in plastic containers fitted with nozzles from which, by gentle squeezing, the contents may be delivered as drops. Plastic containers have several advantages over the glass dropper combination, such as minimizing the risk of the contents being contaminated with microorganisms by the replacement of the dropper, which may have become contaminated by touching the infected eye or any other surfaces. Also, plastic containers are cheap, light in weight, more robust to handle and easier to use than glass dropper type containers. However, there are some disadvantages of plastic eye drop containers. Some plastic materials such as polyethylene can absorb some antimicrobial preservatives like benzalkonium chloride or some drugs. They may also leach plasticizers into the product, or printing inks from the label can migrate through the plastic into the product. It is necessary to conduct compatibility and stability studies to ascertain whether this is likely to be a problem. Alternatives are to use glass or a preservative-free product. The challenge is to develop a packaging system for preservative-free products that maintains the sterility of the product throughout its shelf life and during use. Unit dose systems offer the easiest technical solution to this problem but have the disadvantage of a higher cost of manufacture and of not being as compact as a multi-dose product containing equivalent doses. An alternative approach is to develop a multi-dose preservative-free system. The container is required to be collapsible, and the suckback of air, which could contain bacteria, has to be avoided. Containers are being developed that contains a valve mechanism to achieve this. Due to the safety and regulatory concerns raised by preservatives used in ophthalmic products, there have been efforts to develop new eye drop packaging systems that can remove the preservative from the formulation during administration. Benzalkonium chloride is the most common preservative used in commercial eye drops, and yet there are reports of side effects caused by its frequent use in ophthalmic products. Plastic containers can also be permeable to water vapor and oxygen over prolonged periods of storage. This can lead to gradual loss of liquid product or oxidation of an unstable drug over time. Plastic containers can also be permeable to water vapor and oxygen over prolonged periods of storage. This can lead to gradual loss of liquid product or oxidation of an unstable drug over time. Polyethylene containers are not able to withstand autoclaving and are usually sterilized by ethylene oxide or by irradiation before being filled aseptically with pre-sterilized product. Polypropylene containers can be autoclaved, but are not as flexible as polyethylene for eyedropper use. Semi-solid products have been traditionally packed in collapsible tin tubes. Metal tubes are a potential source of metal particles in ophthalmic products, and so the tubes have to be cleaned carefully prior to sterilization. Also, the final product must meet limits for the number of metal particles found. Plastic tubes are not suitable because of their non-collapsible nature, which causes air to enter the tube after withdrawal of each dose. However, collapsible tubes made from laminates of plastic, aluminium foil and paper are a good alternative to tin tubes. Laminate tubes fitted with polypropylene caps can be sterilized by autoclaving, whereas tubes fitted with polyethylene caps are sterilized by gamma irradiation. The tubes are usually filled aseptically, sealed with an adhesive and then crimped. More detailed discussion on the packaging used for sterile products will be available on the topic of parenteral preparations. Here is the list of important references used for this topic. By now, you should have a whole picture of what is an ophthalmic product and what to consider in formulating it. Thank you for your attention again. See you on the next topic. Bye.